afternoon, everybody. I hope you are having good time with masters. My name is Surya Talari. I am a staff application engineer at Microchip in APIT department. My main focus is DC-DC power management products, power modules, power controllers, and super switches, which are integrated power products. Mostly I concentrate on the constant on time controller, which is the main subject of this class today. So, I will tell you a very easier way to design a power supply without going through rigorous equations. So, that we will discuss in this today's class. So, the class subject is understanding and designing a switched mode power supply with adaptive constant on time architecture. So, you are here, this class is PC6. This class I am going to share with my colleague Paulo Nora. He is also work on the similar field. He works from the Italy office. So, he will join us after a few slides. These are our main class objectives. When you walk out of this class, you will be able to explain different control mode techniques used in the switched mode power supplies, and you will be able to demonstrate advantages and disadvantages of all control techniques, and as well as you will understand the advantages of constant on time architecture. You will be able to build a power supply using a constant on time controller. You will be able to explain steady state and transient frequency deviations, those are inherent in adaptive COT, optimize feedback and ripple injection. So, those two sections will be covered by my colleague Paulo. This is our class agenda. Initially, we will go over a basic comparison of different control mode architectures available for switched mode power supplies, and we demonstrate the adaptive COT architecture, what advantages it brings, and we will understand the design procedure with the constant on time controller, and we will discuss the advantages of constant on time control as compared to the other traditional control modes. We will also go over the practical measurement techniques that we generally use on the bench while troubleshooting the power supply, and we will go over steady state, transient frequency deviations in adaptive COT, and feedback and ripple injection optimization for better transient response we will go at the end to further optimize the power supply. So, without delay, I would like to discuss the different control mode architectures available for switched mode power supplies. So, the main focus of this class is mainly towards the buck converter, but these techniques can be applied for other power stage topologies like the boost converter or buck boost. So, the traditional buck converter has the input supply, unregulated input supply, and it has a high side switch that toggle on and off and provide the energy to the switch node, and there is a low side switch or a diode that freewheels the energy when the high side switch is off. The inductor and capacitor provide the ripple current and regulated output voltage at the output node. For providing the regulated output at the output node, we use different control mode techniques. One of the popular control mode technique is voltage mode control. This control mode technique was there for a long time. In the voltage mode control, the output voltage is sensed and compared with a reference voltage to generate the error signal. At each clock cycle, the high side switch is turned on and provides the energies to the switch node, and there is also a sawtooth ramp voltage, a sawtooth ramp that compares the error signal. So, whenever the sawtooth ramp reaches the error signal, the error amplifier the switch is closed and the low side switch turns on and pre-wheels the energy through the inductor and output capacitor. So, the main advantages of this method are this is well understood, it has a single loop. So, it is very easy to analyze and there is a large amplitude ramp signal. So, the noise immunity in the voltage mode control is much better as compared to other control modes. But there are some disadvantages with the voltage mode control. If there is any input change or any output change, it has to go through the output node and before it get corrected at the output. Because of that, the loop is very slow, and as you can see, there is a output LC double pole. This adds 2 poles that makes the output response with a double pole with 180 degrees phase shift. So, we need to compensate for that double pole. So, we need a type 3 compensation, that means more equations and more analysis need to be done. We need to place the poles and zeros with respect to the double pole whenever we change the filter or output capacitor. So, it requires tedious work, and if you look at the transfer function from the output to the input, the loop gain also depends on the V in, the factor of the V in. So, that makes if there is a wide variation of the V in, then that makes the calculations much more difficult. So, the advantages of the voltage mode control is a simple loop, but disadvantages is a slow loop and compensation design. And sometimes if the ESR of the 0, ESR of the capacitor, output capacitor 0 is within the limit, we can use output ESR 0 and go ahead with type 2 compensation, but still we need a type 2 compensation. Some of the disadvantages of the slow loop can be overcome with other control mode technique, other popular control mode technique called current mode control. In the current mode control, there are 2 loops. One is the outer voltage loop and inner current loop. In the current loop, the inductor current is sensed and used as the ramp signal instead of the fixed sawtooth ramp. Because of that, the inductor current is sampled, so inductor current looks constant. So, this is also fixed frequency control mode. So, at each clock cycle, the high side FET is on and output current is sampled, and we also need to add a compensating ramp for making it stable and to avoid the subharmonic oscillations. So, whenever the sensed signal reaches the error signal, the output is the high side FET is turned off and low side FET is turned on, and the cycle repeats. There are some advantages of current mode control. As you can see, any changes in the input voltage are immediately sensed by the inductor. So, it get corrected immediately. That because of that, the loop is faster than voltage mode control, and as we are sensing the inductor current, the inductor pole moves away from the double pole location. So, the only pole that is available to be compensated is the capacitor pole. So, it is a single pole output pole, and as we are sensing the current cycle by cycle. So, the current limit is inherent in the current mode control. So, this is the one of the inherent advantages of the current mode, whereas in the voltage mode for the current limit we need to sense the current differently and provide the current limit. Of course, there are some disadvantages with the current mode control as well. Now, there are 2 loops. So, we need to analyze the 2 loops as compared to the 1 loop, it is more calculations, and also for any operation for above 50% duty cycle, we need to add a small compensating ramp to avoid the subharmonic oscillations. So, a slope compensation is required, and because we are sensing the current signal, the signal magnitude is very small, it is very prone to the noise. So, the noise immunity in current mode is less as compared to the voltage mode control, and we still need a type 2 compensation to compensate the output pole. So, we still need the compensation calculations. So, these are the two popular methods used in the industry. I mean, in the current mode there are different versions of the current mode, valley current mode, peak current mode, average current modes, there are many methods. So, out of these two there is also another control mode technique that is popularly being used in the industry is the constant on time control technique. So, in the constant on time, the output ripple is used as the comparing ramp with the reference rather than a current sense signal or a fixed ramp. So, it is a ripple based controller which is our main focus of this class. So, in the constant on time control, the output voltage is sensed and a ripple is being added. There are many ways to get this ripple, we will discuss in the further slides, and the resultant voltage will be compared with the reference voltage, and there is a fixed on time block that generates the on time based on input and output, and whenever the input the ripple voltage falls below the reference voltage, the cycle is initiated and it turn on till the on time is elapsed, and once it turn off the low side switch turns on and freewheels it. So, it is a ripple based controller and frequency will be modulated for regulating the output. We will discuss this constant on time and the advantages of it in the further slides. So, this is the block diagram of a basic constant on time control. The power stage is still same, and we are talking about the buck converter, input voltage source, high side switch, low side switch, and inductor and capacitor. And in the basic COT control there are three main blocks. One is the T-on generator, the minimum off time block, regulation comparator, and SR latch. In the T-on generator block, there is a constant current source charging a capacitor, charging and discharging the capacitor, and other side of the comparator has a fixed threshold voltage. So, the output voltage is sensed and compared with the reference voltage. When the output voltage, okay, let me bring the waveforms. So, here we are sensing we are getting the ripple which is required for the constant on time from the ESR of the output capacitor. So, the peak to peak ripple current of the inductor flows through the ESR and produces the ripple, that ripple used for the control. So, whenever the reference voltage falls below the reference voltage, the ripple voltage falls below the reference voltage, the on time is initiated and this capacitor starts charging this ramp, and this ramp is compared with a fixed threshold voltage VTH. So, when the ramp reaches the threshold voltage, the T-on is done and it turn off the high side switch, it turn off the high side switch and turn on the low side switch. During the same time the Qn discharges the output the T-on capacitor. So, that is how the constant on time works, and there is also a minimum on time, minimum off time that we need for charging the boost trap cap and also sensing the low side switch current sense for the current limit purpose. So, it basically operates from the ripple. So, the basic requirement of the COT, it requires a ripple on the feedback network, on the feedback node to work properly. So, generally we need between 20 millivolts to 100 millivolts, typically we use 70 millivolts of ripple to control this COT. So, these are the main requirements. The feedback ripple must be in phase with the inductor current ripple. The ESR ripple can be used if the ESR magnitude is around 100 milliohms or 50 milliohms. This is the case with electrolytic capacitors for the low cost designs, and minimum off time is often required to recharge the bootstrap capacitor and also for current sensing across the low set FET. There are few disadvantages with the basic COT control because the on time is fixed. The on time, so the frequency varies with input and output. So, as the T on is fixed, frequency changes as the duty cycle needs to change. So, basically there is more variation of the frequency with input voltage V out and load. As you can see in the graph, the V in, as the V in is increasing, as the on time is constant, the frequency starts to drop, and this drop is more than like 50 to 70%. So, that is unacceptable for some of the applications. So, the other disadvantage with the basic COT control is that, as we have seen, we need a ripple on the above the reference voltage. So, the DC operating point is higher than the required output voltage. So, the DC regulation is not very good with the basic COT control, because the basic COT regulates the value of the feedback waveforms. That means relatively poor line regulation, because the amplitude of the ripple depends on the V in magnitude. Let us see how we can solve these issues to get the advantages of the COT control in the following slides. So, now we started using the adaptive COT architecture. Basically we took the basic COT architecture block and we did some modifications to that, and we are calling it as adaptive COT, and let us see how the adaptive COT will solve the basic issues. This is the block diagram for the adaptive COT. So, the architecture is same as the COT architecture, but we did few modifications to the T-on generator block, and also we added something called DC regulation enhancement. That is what those are the issues we were discussing in the previous slide. So, we added this, we modified these two blocks to solve those two issues. Let us see how those the two issues get solved. Let us focus on the frequency first. So, in the basic architecture we have seen a constant current source charging the capacitor. So, in the adaptive COT, instead of this making this current constant, we tap the current source, basically it is proportional to the input voltage. So, those input voltage is derived through a resistive divider, through a frequency pin. In some of our controllers you see the frequency pin. So, basically now the constant current is proportional to the frequency pin input voltage, which frequency pin is in turn proportional to the input voltage. That means the constant current is proportional to the K2, K1 and V in. So, K2, K1 are the constants, they are basically coming from a resistive dividers. And the other modification to the other end of the comparator is the threshold voltage modification. Instead of keeping this threshold fixed in the basic COT, we tap the output voltage from the switch node and apply through a low pass filter and make it vary according to the output voltage. So, one end of the comparator is proportional to the input voltage and one end of the comparator is proportional to the output voltage. So, if you look at this equation, T on is nothing but C T on V naught by K V in. This came from C dV by dt equal to I. So, I derived this equation from that, and we also know that the T on is nothing but duty cycle multiplied by the switching period. So, which is duty cycle equal to V naught divided by V in. So, if you combine these two equations, C T on V naught divided by K V in equal to V naught divided by V in multiplied by T s. If you further simplify this equation, the switching period T s is proportional to or equal to C T on divided by K, where K is the constants derived from K 2, K 1 and K 3. So, that means that the switching period is independent of the input voltage and output voltage. It depends on a capacitor and some constants. This and the C T on is fairly constant, it is internal capacitor on the on chip capacitor, it is fairly constant. So, the switching period remains very constant in the adaptive COT architecture. So, the other modification we have done to the basic COT architecture to solve the DC regulation issue is adding of this block, the DC regulation enhancement block. So, this block actually contains a operational transconductance amplifier, high gain transconductance amplifier with unity buffer bypass filter. Basically, it is a active low pass filter. The purpose of this block is that we know that the regulation comparator requires a triangular waveform for regulation. So, this amplifier along with this bypass filter, it transfers all the AC ripple from the feedback node to the output of the amplifier. It does not provide any phase or gain modification to this, it only provides the DC gain, it does not provide any AC gain. It is like a active low pass filter. Let us see how this OTA improves the regulation. So, basically the purpose of the OTA is to forward all the AC ripple and provide the DC gain for the provide the gain for the DC component. So, I redraw this same figure here, the feedback node and the output of the GM amplifier, and this is the main regulation comparator and the same reference voltage is used. So, in some of our data sheets you see a compensation, the block named compensation. It is not actually a compensation, it is actually a low pass filter with a buffer. It is a capacitor, integrator and a buffer. To protect the IP, we named it as a compensation block. So, the comp input is nothing but V ref plus V peak to peak by 2. V peak to peak is the peak to peak ripple of the this voltage which we needed for the regulation. And if you look at the feedback node, V comp minus V ref divided by gain of the OTA. So, that means that V feedback will become V peak to peak by 2. So, the gain of the OTA is in the order of 10,000. So, the feedback ripple AC ripple will become 100, let us assume that peak to peak ripple is 100 millivolt for a typical application. So, for 100 millivolt the V feedback AC ripple is going to be 100 millivolts divided by 10,000 which is 0.1 millivolt, which is very much negligible. So, that is how this operational transconductance amplifier block which we added to the adaptive COT improves the DC regulation and it makes independent of the input voltage. So, OTA improves the DC regulation. That is how we in the adaptive COT architecture we solve the issues those are presented in the basic COT architecture. So, these are some of the performance measurements we have taken on one of our controller MIC 2103. It is a 75 volt COT controller for different applications. So, the V out equal to 3.3 volt, I out to 2 amps, input we varied from 5 volts to 40 volts and the programmed switching frequency is 550 kilohertz. As you can see the switching frequency variation over the input voltage range is very less, is plus or minus 20, maybe less than 20% as compared to the main variation which is coming big variation coming in the basic COT architecture. Even in the adaptive COT, the for certain output input conditions the frequency variation will be little larger, especially when output voltage is low, 1 volt or 0.8 volt. So, those intrinsic effects will be discussed by my colleague Paulo in the next slides. So, but for some output voltages, higher output voltages, the switching frequency stays relatively constant irrespective of the input voltage and output voltage and also the load. The other this is another performance metric we have captured from the same controller. This is a total regulation versus input voltage. We also varied the load from 0 amps to the 12 amps. It is operating at 600 kilohertz nominal, and the total for output condition of 1.2 volt, the total regulation by after varying the input voltage from 5 volts to 35 volt comes less than 0.2%, which is pretty good. So, the frequency variation with V in and V out are improved, and the total regulation is also improved in the adaptive COT architecture. So, I would like to get your attention by asking this question. So, which control method you typically want to choose for a 75 volts to 0.8 volt single stage conversion, not multi-stage, single stage conversion operating at certain frequency. So, you have choice of voltage mode control, current mode control, and constant on time control.
Probably not B.
Yes, it is not B because of the delays in the current sense loop. Yes, you are right, current mode control we cannot choose. Even if we choose the voltage mode control, from lot to lot the minimum controllable on time varies. So, if you choose the voltage mode control, one IC may regulate 75 volts to 0.8 volt based on its minimum on time, but in the future it may not able to regulate because it reaches the minimum on time. But if you go to the constant on time control, the frequency modulates. The frequency does not stay constant, but in the case of voltage mode control, the frequency try to stay constant, does not affect, but once it reaches the minimum on time, it cannot control anymore. But in the case of constant on time control, when it reaches the minimum controllable on time for that particular IC, whatever it could be, if still the output is not regulating, it can modulate the frequency, and still frequency variation will be there, but at least the output is still within the regulation 0.1% or 0.3% whatever we wanted for the load. So, that is why for a lot of our controllers and also our products, we allow 75 volts to 0.8 volt single stage conversion. In a lot of our data sheets, you can see the efficiency curves also given for this 75 volts to 0.8 volt. Okay, so now we understood the adaptive COT architecture. Let us work on the design, how we can design SMPS with adaptive COT architecture. So, first we will discuss we will concentrate on the control mode, not the power stage. The power stage design, I think you already might have went through different classes, how to select the inductor. I have given the equation there. Basically it depends on the input and output, and also how much ripple current we can accept. Generally it is 30%, and the output capacitor is selected based on the how much steady state ripple the transient ripple we can allow at the output, and the switches are selected based on the input voltage rating and also the RMS current that goes through this. But we will concentrate mostly on the control portion of it, how to design the control system for work with the constant on time architecture. So, the one we already know that the regulation comparator needs enough good ripple, which is 20 millivolts to 100 millivolt. So, the ESR ripple, the ESR is inherent in some of the capacitors, like the electrolytic capacitors. So, if you are using electrolytic capacitors for your application for the low cost solution, the ESR, you can make use of the ESR of the capacitor to get the enough ripple to make the system stable. You do not need anything else, any type 2 compensation, any compensation or any ripple injection for the for those type of applications. So, make sure that your ESR 0 is less than the switching frequency. So, now we will understand the how to make the COT system stable for different output capacitor chemistries. So, I mean inductor can be the power stage can be designed the same way how you design for any power system, either voltage mode control, power current mode control or any control mode. You design your power stage based on your load requirements and your input requirements, that does not change. But for example, if you are using electrolytic capacitors for your application because of the cost reasons, you can make use of the ESR of the output capacitor to make the system stable. So, when you are using electrolytic capacitor, the ESR ripple is very high and is almost in phase with the inductor current ripple. And if you look at the capacitor component, the capacitor component for those electrolytic capacitors, because the value is very high, the capacitive component is very less as compared to the ESR ripple, and it also lags. So, if you take the vectorial diagram for these two ripples, so this is the inductor current, the x axis, and inductor voltage, capacitor voltage. So, the capacitor component is the magnitude of the capacitor component is very less and lags the inductor current by 90 degrees, and the ESR ripple is in phase with the inductor current, and also the magnitude is high. This is the case with electrolytic capacitors. So, if you take the vectorial sum of these two components, the feedback voltage which is getting injected to the feedback node is almost in phase with the inductor current. So, in these type of applications, no external ripple injection is required and your system is stable without adding any more components. So, you do not need to design any ripple injection network or anything like that, but this is only for the case where the ESR of the output capacitor is in the range of 50 milliohms to 100 milliohms and above. And again, for the low cost solutions, people generally use electrolytic capacitors only. But in the modern days, the high performance loads require the very small ripple at the output, like 1%, within 1%, the steady state ripple cannot exceed 1% of the output voltage regulation, output voltage. For example, if it is 1 volt, so you need 10 millivolt. So, in that case you cannot use electrolytic capacitor, you need to use tantalum capacitors or ceramic capacitors. If you are using a tantalum capacitors, they have some ESR as well. So, the ESR will be in the range of 10 milliohms to 50 milliohms. So, to get the ripple from these the low ESR capacitors, we recommend to add a feed forward capacitor from the output to the feedback node. So, basically this feed forward capacitor, what it actually do is it adds a 0 and a pole and provides a phase boost in the mid frequency and high frequency gain. The DC gain did not change, DC gain still R2 by R1 plus R2, but this feed forward capacitor, it adds the high frequency gain and also provides the phase boost, and it bypasses all the ripple from the feedback on the output to the feedback node. So, this is the case with low ESR capacitors or the tantalum capacitors. So, there is another type of capacitors we generally are using for the high performance loads are the ceramic capacitors. In some cases you need to use only the ceramic capacitors because of the height profile requirement and also for the output voltage ripple requirements. So, in that case we need to extract some ripple from somewhere, and one of the node that is good for extracting the ripple is the switch node. So, we need to connect a ripple injection network from the switch node to the feedback node. So, the RI and CI, the injection network, provides it integrates the voltage, the rectangular voltage from the switch node, and provides a triangular waveform at the feedback node. So, the feedback node requirement for this is the injected voltage to the feedback node from the switch node is V in multiplied by d 1 minus d divided by the time constant. So, in this case this CB is a blocking capacitor. As a rule of thumb, we always use 0.1 microfarad, and as a rule of thumb these injection capacitance we tend to use 1 nanofarad or 2.2 nanofarad like that, and Ri, the injection resistance, we calculate based on this equation. So, what we make sure is that the impedance of the injection capacitance is less than the R1 and R2. R1 and R2 you select based on your output voltage requirement. Based on the reference, generally we have 0.8 volt reference, and you select the R1 and R2 how much voltage you need. So, if you satisfy this equation, basically to bypass all the output ripple to the feedback pin, and we also make sure that the blocking capacitor value is much higher than the CI. Generally we choose 0.1 microfarad as a rule of thumb, and the CI is 1 nanofarad. So, those are the typical values we recommend in many of our products. And the other thing we ask you to make sure is the time constant provided by this the feedback network impedance is greater than the switching period, because we want a triangular waveform at the feedback node. That is why we ask you to satisfy this equation. So, there are two ripples coming from the ripple coming to the feedback node. One is from the switch node and one is from the feedback from the output node. So, this is the case only with the ceramic capacitors. If you have a electrolytic capacitor, then you may not need this. So, let us say let us understand the superposition of these two waveforms. So, one is coming from the switch node to the feedback node, and other is coming from the output. So, to understand what is coming from the switch node, let us ground this node, output node, so that you can see it is a RC network. So, this is the amount of the ripple coming to the feedback node, and we call it as feedback 1. And when there is no ripple at let us assume that there is no ripple from the LX node, and all the output ripple is coming to the feedback node, let us call it as feedback 2. So, if we superposition these two voltages, you can see that V feedback 2 lags the inductor current, V feedback 1 from the switch node leads the inductor current, but if you take the vectorial sum, it is almost in phase with the inductor current, which is the basic requirement for our COT to be stable. So, that is how we make the COT controller stable with different capacitor chemistries. Again, I would like to get your attention which control method to choose for ease of control design. Voltage mode control which requires type 3 or type 2, current mode control, slope compensation, and constant on time control. Again, it depends on your output capacitor chemistry. Okay, so for the ease of control control system design, we won't want to go through lot of equations. So, the voltage mode and current mode are not preferred. The constant on time control is more preferred. So, this is a typical block diagram for the type 3 compensation with a voltage mode control. This is a remote sense amplifier with gain unity gain, and this is this network, this RC network, and this one is a type 3 compensation. So, you can see the transfer function DC gain block, the error amplifier transfer function 1 plus S by ZY SC1, 2, so 2 zeros, 2 poles, 3 poles with including the origin and origin pole, and then the modulator gain, the ramp voltage, and the power stage filter. So, there are lot of equations, lot of transfer functions we have to analyze. These are standard, but we still need to analyze. We need to for every input output conditions, we have to go through these tedious equations. So, all the above equations can be avoided with the constant on time control because of its simple nature in the control system design. So, let us go through the how to design the control system design. You select your output capacitor based on your ripple requirements, and make sure that your if you are using a electrolytic capacitor with good amount of the ESR for your if your application accepts it, then make sure that your ripple voltage, ESR ripple voltage is 100 millivolt, and also make sure that the ESR ripple is more than either 20 millivolt or 4 times the capacitive ripple component, then no external ripple injection is required. So, your control system is done, that much easy it is. So, if you are using electrolytic capacitor with good amount of the ESR, it is very easy, you do not need to go through any equations. Once you select your input filter, switch, MOSFET switches, and inductor and capacitor. If for example, if you are using a ceramic capacitors or the low ESR capacitors, then you need to remember this equation for injecting the ripple to the feedback node. So, we generally select the feed forward capacitor from output to the feedback in the order of 1 nanofarad, 2.2 nanofarad, and 4.7 nanofarad. You can choose either one, and you can calculate the ripple injection resistance based on this equation. In most of the cases, as a rule of thumb, the blocking capacitor is 0.1 microfarad, that is what we recommend. It makes the system stable for wide variety of input voltages, but still there is still some optimization is possible by varying this blocking capacitor value. I think further optimizing the transient response will be discussed by my colleague. So, this is a typical controller analog controller application. So, you can see this is one of the controller MIC 2164, and it has the drivers inbuilt. It is a COT controller. The usual functions available are enable feedback node, input voltage, low side driver, high side driver, LX, and boost trap switch. So, this is a snubber. We generally use the snubber in all the buck converters. I mean, we recommend the snubber because if your application is noise sensitive, then it is better to add a snubber, unpopulated snubber, and based on your results you can optimize it. And we also recommend a series gate resistor to slow down the FET in case if your application is noise sensitive. But these are common for any controllers. The main ripple injection network to the application is the R injection and the blocking capacitor, which is 100 nanofarad, and the CFF. So, only these 3 components you need to select if your output capacitor is only ceramic, and the CFF is generally, as a rule of thumb, as I said, 2.2 nanofarad, and only thing that need to be calculated is R injection. So, in some of our products we have internal ripple injection where the input and output variations are very much limited. For example, if it is a 5 volt out 5 volt input 5 volt bus application, your output is also very much limited. Then we can integrate these ripple injection components inside the IC. So, you do not need to add the ripple injection network outside of your application. So, this is usually available in low power DC-DC converter applications, but when we have wide variation of the input voltage from 4.5 volts to 75 volt, which is the case with all of our COT controllers. There are family of controllers from 4.5 volts to 75 volt, different generations of the controllers, and based on the controllers we also built integrated FET regulators. Now, so in all those products, because the input variation is very wide, we keep this network outside, but in the low voltage controllers, low voltage applications, we integrate this ripple injection network. One of the example is MIC 23030. So, let us understand the advantages of the COT architecture. I mean, we discussed how we designed the COT architecture. So, transient response, COT versus the fixed frequency controller. One of the major advantage of the COT controller is the transient response, because it does not have any clock to fix the transient the clocking instance. So, whenever there is a low transient, when output voltage starts to fall, it immediately initiate a pulse to correct the output, and it applies the minimum T off, as we discussed in the beginning of the slide. The minimum T off is required for charging the bootstrap cap, high side bootstrap cap, and also for sensing the low side current limit, because if you are using a low side current limit for protecting the IC, we need minimum off time for the low side, so that it will get the enough signal, so that the circuit is protected. So, it applies the minimum off time, it is generally in the range of 200 nanoseconds. It applies the minimum off time, and if the output voltage is still below the reference, it immediately initiate another pulse. It does not wait for the another clock cycle, because there is no clock. It immediately initiate the another clock cycle, and so on till the output is get corrected and comes to the within the regulation window. So, the switching, because of this, the switching frequency is increased during the low transient, and pulse width does not change, because your input and output voltages did not change. Output voltage is changing little bit, but not much. So, the pulse width is still within the approximation window, and the response delay is only T off, which is 200 nanoseconds. Let us take the example of a fixed frequency controller like voltage mode control. So, whenever there is a low transient, if it happen, for example, if it happens in the middle of the clock cycle, middle of the pulse, it wait till the next cycle to correct it. So, and once it reaches the next clock cycle, it increases the duty cycle, and once the clock cycle, once the pulse width is done, it again wait for the next clock cycle. So, because of this, the only the duty cycle during the low transient conditions for the fixed frequency controller, only the duty cycle is increased, and it also depends on the loop crossover frequency. The switching frequency is almost constant in this case. So, the response delay can be as bad as 1 clock cycle. So, I mean, that is the major advantage of the COT controller for the transient response. Okay. Again, I would like to get your attention. I am sorry, I kept lot of questions because it is after lunch. So, that is why I would like to get your attention. Which control mode to choose for a smaller solution size, provided you have a big transient response requirement in your circuit. So, again voltage mode control, current mode control, and constant on time control. For a given transient condition, say 5 amps to 10 amps with a certain slew rate, you need to select the output filter to correct your output voltage. So, voltage mode control, current mode control and constant on time control. So, again the voltage mode control, the bandwidth is generally 1 by 20th of switching frequency. Current mode you can go as fast as 1/5 of switching frequency, but constant on time control there is no clock. So, it is a open loop system, theoretically it is a infinite bandwidth. So, you try to correct the output voltage immediately whenever there is a change in the output voltage. So, your requirement of filter at the output is very much limited. So, because the output filter takes the major solution size in the application. So, the constant on time control gives a smaller solution size. So, another inherent advantage of constant on time architecture is the light load pulse skip or the light load efficiency, because if in the voltage mode control and the current mode control there is a amplifier in series with the path. So, whenever they go to the light load, they generally they provide another comparator and skip the usual path to make it light load efficient, but the transition is not smooth. But in the case of constant on time, there is no amplifier in the path and there is already comparator in the circuit. So, that comparator we make use of it to get the pulse skip mode. So, in the pulse skip mode, when the output voltage falls below the reference voltage, it initiate a pulse at the switch node for the high side by turning on the high side, and after the T on is done, you turn off the high side and turn on the low side FET. Once the low side, once the inductor current reaches the 0 level, the 0 current comparator turns off both the switches and it enter into the low quiescent current mode, and the output voltage starts falling until it reaches the reference voltage. Once it reaches the reference voltage, again another pulse is initiated. So, during this period the quiescent current is reduced to very large extent, because we turn off the drivers as well as we enter into the low Q mode. So, that is why the pulse skip mode is very much inherent to the constant on time architecture, and also the transition from the light load mode to the full load mode is very smooth and very fast. Okay, so, the same thing I wrote here, pulses charged to coil and cap which bumps up the output voltage at a fixed frequency. When coil is fully discharged, output cap delivers the current to the load and the whole internal circuitry is shut down for ultra fast turn on and off. The pulse skip mode is much faster in the COT due to fast comparator in the loop. That is the inherent advantage with the COT. So, let us go over some of the practical bench measurements techniques and the PCB layout guidelines while working with these controllers. I mean, these are applicable for other products as well. These are the general practical measurement techniques. So, measurement of the voltage spike. So, we generally try to measure with the oscilloscope probe, but if you keep the probe ground loop somewhere further from the output node, then the oscilloscope probe loop inductance can create spikes on the output voltage. That is not the real way of measuring it, but for example, if you are powering up a ADC or anything sensitive loads, so your ADC measurement can get messed up, because if there is a ripple, if there is a high frequency noise, but how high frequency noise we have on the output, we need to measure it accurately by proper method, so that we can take necessary measures if at all, if you want to reduce it by adding the snubber as we discussed in the controller block diagram, or increasing the BST resistance to slow down the FET. Those things we can do, but before we do that, we need to understand how much ripple we exactly have on the output. So, the best way to measure the output ripple is to use the method like this with a small ground loop and place right across the it is called barrel method. So, place across the output ceramic capacitor to measure the output voltage. So, the other measurement we generally do in the control, any control system, is the measurement of the loop parameters, loop gain and phase. So, one way to measure is using a board analyzer or network analyzer, and we generally break the loop at one point. Generally, we choose the output voltage node, and we add 20 to 50 ohms and inject a signal from the signal source through isolation transformer, and we measure we let that signal pass through the loop, and we take the resultant signal, and we take the ratio of the injected signal to the measured signal and plot the Border plot. So, this is same in even for the COT controllers. We break the loop and we do the measurement as usual with any other controllers. So, one of the other measurement we need to do is the thermal measurements. In lot of our data sheets, we denote the junction to ambient thermal resistance and also junction to the case thermal resistance. You can measure the thermal ambient temperature, and if you know how much power it is getting dissipated in your package, you can calculate the junction temperature of the IC at that particular operating condition by using this equation. But if you can measure the case temperature and you also have theta Jc on our data sheets, you can calculate the thermal maximum junction temperature by using the second equation. So, the case temperature can be measured with thermocouples or the infrared cameras, FLIR cameras. So, this is one way to do the thermal measurements in the lab. So, other important point is the PCB layout. So, in the PCB layout, in any control mode technique, we always place the power components first, the low side switch, high side switch, all the inductor, capacitor, high current paths, we need to place them first and then route them and always use a ground plane, second layer as the ground plane for better noise immunity, because there are a lot of switching currents at the input and at the switch node. So, provide good bypass capacitors at the input as well as the output, and always route the signal traces away from the high current switching nodes, especially these because the COT needs the ripple coming from the switch node. So, make sure that they are routed away from the switch node, make sure that there is not going through underneath the inductor or anything like that. And wherever possible, separate the power ground and analog ground and have them star connected, and place the gate driver close to the MOSFETs if you are using separate MOSFETs. We also have some integrated FET products, there you do not have to the routing becomes little easier with some of the products, but if you are using a controller, it is better to follow these guidelines. So, summary of this class, whatever the slides I have discussed. So, we have discussed the advantages of the constant on time, the one advantage, the major advantage is easier loop design. So, I have seen one equation to calculate the ripple injection network. So, that if you are using a ceramic capacitors or no equation at all, because if you are using a electrolytic capacitors, then you do not need to remember any equation or any type 2 compensation or type 3 compensation. So, the loop design is much easier, and it is also any capacitor stable. You do not need to limit to your output capacitor to certain chemistries. You can use any capacitor, it becomes stable. And the major advantage is of the constant on time control is ultra fast loop transient response, providing best in class transient response in a half a cycle. So, that is not the case with any fixed frequency controllers. And other inherent advantage we get from the COT controllers is the hyper light load efficiency, and this is very much required for battery powered systems where light load efficiency is much better. That is why people use COT controllers in the mobile laptops. I mean, some of the controllers they use are COT controllers for the laptop power supplies. Again, I would like to get your attention before I finish my slides. So, which control method you choose for synchronizing to external clock? For example, if you have multiple power supplies and you want to minimize the EMI in the system and you want to connect to external clock to all of your POLs, which control method you choose? So, in the voltage mode control and current mode control, there is a clock. So, that is the reference clock. You can synchronize to the external clock, so because there is a reference, but when it comes to the constant on time, there is no clock in the system. So, it is difficult to synchronize to the external clock. So, that problem has not been solved for the COT unless we use another PLL in the loop. So, that complicates the design, but as of now we do not have any products that has that we can synchronize the external clock to the COT controller. That problem has not been solved yet, but if you are okay with some little frequency deviations, I think the COT controller is best, but for controlling to the synchronizing to the external clock, the voltage mode control or the current mode control is generally chosen. So, that ends my my slides. I would like to transfer the remaining session to my colleague Paolo Nora. Unless you have questions.
What was the highest operating voltage that your parts can do?
Right now 75 volts.
75 volts.
4.5 volts to 75 volts. The input voltage variation on those products are 4.5 volts to 75 volts.
Is there any difference between the COT and like a hysteretic controller?
It is kind of hysteretic controller. It is a ripple based controller.
Okay.
Any more questions, please? Thank you very much for your attention.
Hello everybody. Hello everybody, I am Paolo Nora. I will be dealing with the last two sessions of this presentation. In previous slides, my colleague was showing the frequency curve over line voltage of our adaptive constant on time controller, the MIC 2102. And you might have noticed that there was still some residual variation of the frequency. So now in steady state frequency deviation of adaptive constant on time, we are looking into the reasons for those deviations and find the root causes of them and how maybe also to alleviate them. So the basic fact is that adaptive constant on time is only trying to emulate the behavior of a fixed frequency PWM part. For any type of switching converter, we can write that the on time is the duty cycle times the switching period. But only in the case of a lossless buck converter, we can also write that the duty cycle equals V out over V in. In the case of an ideal on-time generator that makes the on-time rigorously equal proportional to the output voltage over the input voltage, then we can change the two equations and conclude that our frequency will not change over line and load or output voltage. But the on-time generator is not ideal, and also the buck converter has losses. That's why we are so concerned about efficiency, because of the losses. So let's look at a simplified model of the lossy buck converter. So we are taking only resistive losses into account here. So losses, they mean drops, resistive drops due to current. And what the control needs to do in order to keep up the voltage conversion ratio is basically to deliver a higher value of duty cycle with respect to the lossless case. Here we can see that the duty cycle value has to increase as the load current increases. So if we keep generating our on-time with a simplified model V0 over Vin, what happens is that we are delivering an on-time which is less than it's needed to keep up the duty cycle. So the end result is that instead of having the frequency curve flat over the load current, the frequency tends to increase as the load current increases. And this effect in reality can be, it obviously depends on the losses in the circuit, so a more efficient circuit will exhibit this effect much less, but it can be in the range of 10% or even more. It's not just a few percent as in the simplified model. Now, is there a better way of doing things? And yeah, there is a better way of doing things, which is what has been implemented in our controller. So instead of looking directly at the output voltage in order to generate the on-time, we are looking at the switch node. We attenuate down the switch node waveforms and we apply fairly heavy low-pass filtering. The benefit of doing this is that now we are also accounting for the DCR of the inductor. That leads to a reduced frequency deviation as the load current increases. So instead of following the red curve, we are now following the blue curve. So we are gaining some percent in frequency stability over the load range. Well, there is one limitation when you do that. So on your IC controller side, you always have to connect the switch pin of your controller to the inductor. There could be one case where, for example, you want to put an half-bridge driver in between in order to drive beefier MOSFET to crank up your power throughput capability. So you may think, okay, I can ground the switch pin on the controller, use the high side output from the controller, connect it to the high side input of the driver, and use the controller that way. But you cannot, because what will happen is that the on-time generator will see an output voltage very close to 0. So the generation of the on-time will go basically to its minimum value, and the switching frequency will go to some crazy value. And I've been burnt by this problem myself. The advantage is, of course, is that you are freeing up one pin for other purposes. So if you are pin limited, then this method of doing things frees up one pin in the controller. The on-time generator itself is non-ideal. It has to work, this comparator, this poor comparator, has to work with an extremely wide range of output voltages. You want to be able to set your output voltage maybe from 1 volt up to 24 volt. So obviously the input common mode range of this comparator plays an important role. Its offset voltage determines an uncertainty band around the threshold voltage. It also has a finite response delay. And the presence of a finite response delay, also the slope of the signal across the on-time generation comparator plays an important role. Let's look at the low output voltage issues first. There are limitations to the lowest usable output voltages. I said the offset voltage generates an uncertainty band around the switching threshold, as well as ground shifts and noise. The bottom line is you cannot expect to generate an on-time which is accurately proportional to the ratio you want all the way down to 0 volt. So when this threshold approaches 0 with all these uncertainty factors, the proportionality will not be there anymore. So, and there is indeed one operating condition during normal converter operation where you are working with a voltage which is extremely close to 0 volt. And that is namely the beginning of the soft start. So here we are seeing the behavior of a constant on-time controller during a closed loop soft start. The on-time is generated, the regulator attempts to follow the reference, but neither the shape nor the frequency are what you expect to be a steady state. That's the limitation you have at low output voltages. We can look at the limitation of the high input voltages. In many of our parts, you can see that we recommend the output voltage to be set up to a certain number of volts, for example, 24 volts in the 2101 to 4 family. Where is the limitation coming from? It comes from the common mode range of the comparator. These comparators, because they have to work with also with a very low value of thresholds, they are typically designed as a PMOS input stage. So we have an analog supply voltage. We have to provide some headroom for the tail current source of the differential stage. And we have the gate to source voltage of the differential pair. So we end up with the maximum value that the threshold voltage can reach, and through the internal attenuation factor, we can determine the maximum output voltage value that we can safely support. And as you can see, there is a trade-off, because bigger attenuation will let you support higher and higher output voltages. But then what happens at the other end of the output voltage setting range when you're trying to regulate 1 volt output? Then your threshold will be very close to ground, and then the frequency accuracy at low output voltage setting will suffer a lot. Now, we want to explore a little bit more issue related to variation of input voltage. In the presence of a fixed delay, the delay may also depend on the overdrive of the comparator, but for now we will assume it's a fixed delay. So we can see that with a fixed delay, the point at which the comparator will switch, let's say this is our threshold, and we have 2 different slopes of the on-time generation capacitor signal. You can see that in presence of a faster slope, we are generating a bigger error. So basically, our on-time generator is increasingly bigger than needed as the Vin increases. That means the frequency will tend to decrease as the input voltage increases. And this effect may not be that bad if your on time is already relatively big, because the delay doesn't count much if the on time is already big. But if we are trying to set the output voltage to a very low value and the on time is already very short, then this effect can become much more pronounced. So we have a deviation of the frequency of roughly 200 kilohertz over a nominal value of 600, so 30%. Now, simple, very simple one. This one, in light of the curve that we just saw in the previous slide, what is, in your opinion, the worst case output voltage setting with respect to frequency deviation for an application using our controller and with an input voltage range ranging from 18 to 36 volt? Is it 3.3 volt, 1 volt, or 5 volt? One volt, yes. The lowest output voltage setting will be the most sensitive to frequency deviation due to line effects. We want to also look a little bit in further detail about the frequency deviation, the transient frequency deviation of adaptive constant on time, and to make a couple of additional considerations. As my colleague Surya mentioned, the biggest advantage, probably I wouldn't say probably, certainly, the biggest advantage of constant on time architecture is its superior low transient response. It's a control mode architecture which is very popular in the industry, and this is the main benefit. So during a load step, you basically increase momentarily the pulse density, the repetition rate of the on time. You have this momentary switching frequency increase, and this scares a lot of users because many users are concerned about EMI spectrum or frequency variation. This can be a big concern for many users. However, there are two important considerations we should make. First one is that the on time itself is not changing significantly during the load transient because the input voltage is constant and the output voltage is also kept relatively constant by the control itself. And we have a clearly stated minimum off time specification from the datasheet. So at the end, we can put a safe number on the minimum switching period. Even if the control is fully saturated, the minimum switching period will never be shorter than whatever T-on we have in this input-output voltage condition plus the minimum off time. So it is true that the frequency changes. It is also true that the frequency will not go crazy. We look at the other side of the load transient, so the load release. And for load release, well, what a constant on-time part does, the output voltage, so the feedback, goes above the regulation threshold, so it has to wait for the output voltage to recover to hit the regulation threshold again. At the end, what we will see is that the part will stop switching for a few cycles, and then it recovers its steady state frequency at the new load current value. But what would any fixed frequency PWM controller with 0% duty cycle capability do if you push its bandwidth to the limit and you have a very sudden load release? Well, it will go to 0% duty cycle. So it will also stop switching. Here we are showing what fixed frequency valley current mode part does with the same load release. We have been compensating this part more aggressively to get a faster transient response, and the behavior is basically the same. So when it comes to aggressive requirements with respect to load transient, and we are pushing the bandwidth of our fixed frequency controller, there is no real difference in behavior of the instantaneous switching frequency during load release. Now, the last topic we want to cover is that we've seen that in the case where you need to add the ripple injection network, which is almost always the case because in modern point of load application you will have some significant amount of output capacitance, maybe parallel to polarized capacitors, but the ripple needs to be low in demanding application. So that's the case where we have to add these two components actually, and one is a fixed 0.1 microfarad capacitor, the DC blocking capacitor that Surya mentioned. Well, we are adding a couple of more components, so maybe there is some room to optimize things. Unfortunately, optimization requires modeling homework. heavy modeling homework. And ripple-based controllers are not easy to model at all, because all the, let's say, legacy averaging methods we have to analyze switch mode converters, like, for example, the PWM switch model, work by removing the ripple. Now, we cannot apply this method if the ripple is so important to the regulation. There are alternatives to modeling of ripple-based controller. Sampled data, which was described in a very good paper by Mr. Redl, is a suitable way of modeling ripple-based converters. And there were, over the last few years, a bunch of interesting papers coming from the Center for Power Electronic Systems of Virginia Tech using describing function methods. You can also look at the constant on time on another side. So you can look at the constant on time control as a variable frequency control, where the off time is being modulated by the controller and the on time is being modulated through the on time generator. And there is the so-called ENACE space state averaging method described by Mr. Privasser and others. And this method has been recently applied to the modeling of constant on time by the University of Salerno in Italy. Now, we don't want to go or to rely to any of this stuff. It's too complicated. We take a more practical approach, and we start looking at our stage with the ripple injection network, and we derive all the expressions without digging into this block, which combines the power stage plus the control. Power stage and modulator are lumped into a single block, and we don't want to deal with it. We don't want to analyze it. We go through the analytic expression of the loop gain, and keep in mind where this AV term is. Now, what do we do about AV? We measure it. So the Bode analyzer can also measure fairly well, I would say, transfer function if we're hooking the receiver input to a switch node. So, for example, a PWM output. And what we did here, we hooked the receiver input to the switch node, and we're looking at the transfer function from the feedback to the switch node. Well, it's kind of noisy measurement, so the phase may look crazy, but this measurement tells you one important factor. The magnitude of this measurement tells you one important factor, that AV looks like a high gain amplifier to a fairly high frequency, up to a fairly high frequency. So bottom line, AV is big. So the previous expression simplifies in this one, where we highlight this red ratio, and this red ratio is the ratio of the ripple injection impedance to the upper portion of the feedback impedance. So this ratio matters to achieve more loop gain, higher loop gain at low frequency. And this is a very important thing to have if you're concerned about the low transient response quality. It's not just a matter of loop gain bandwidth. Here we are comparing two different transient responses. One is basically the same power stage, different compensation, let's say selection of ripple injection and feedback components. The first one has a crossover frequency around 72 kHz, but the loop gain at low frequency is very, very low. The second one has a little bit lower crossover frequency, but has a much, much better and higher loop gain at lower frequency. And here you can see how the quality of the low transient is so much better in the case of a higher loop gain at lower frequency. Here in this measurement, our output voltage setting, you may not see it, but was around 3 volt, I would say 3.3 volt. Now what happens in simulation with the output voltage setting around 1 volt. Here we keep the ripple injection impedance the same, and we are changing the impedance level of the feedback impedance. So we see that in the case of a higher impedance level, we have the red curve. In the case of a lower impedance level in the feedback impedance, we have such a much better behaved low transient response. And the improvement is around 36 millivolts. So, and exactly for the same setup, we go to experimental measurement, and we see a very close number for the low transient improvement by setting the feedback impedance to a lower level. It's 4.2%, which is quite a bit at 1 volt. And so, key takeaways from this optimization discussion. When you have to use ripple injection because you have some ceramic output capacitor at the output, always try to maximize the ratio of the ripple injection impedance to the feedback impedance for improving the low transient. What does it mean in terms of self-injected ripple amplitude? The self-injected ripple amplitude should be as low as possible, or as low as practical. Don't forget that constant on time is a ripple-based control, so it's very sensitive to noise jitter. So if you are lowering and lowering the feedback ripple amplitude, you will end up being more jittery or more noisy. And in any case, you always have to keep in mind stability criteria. So for stability, the feedback ripple amplitude has to be bigger than 20 millivolt, or at least 4 times the capacitive component of the ripple voltage at the feedback node. So as you can see, is a semi-empirical approach, but it can give you some significant improvement over the basic design. So that concludes my section. And any questions? No questions? Okay. Yes.
That first point, maximize the ratio CB over ZF. Is that thing kind of understood why it helps?
Yes, because it increases the loop gain at low frequency. It comes as a factor in the expression of the loop gain. So is a...
Go back to that slide where...
Yes, sure. Here. So let me go through it again.
One more slide back.
Yes.
Yeah, this one.
So what happens is that after we verify that AV is a big number, basically we can neglect all this term respect to ZF over ZB, and then after we say this is 0, then the gain, loop gain, simply becomes minus ZB over ZF times this factor. I hope I answered your question.
Would that imply that the best response is achieved without any ripple injection relies strictly on the output ripple?
The best response without any ripple.
ZB is, well, when there is no ripple injection, ZB is infinite, right? So you get the highest gain.
Well, if you are not injecting ripple, you'll end up in stability problems, because we are dealing with...
I assume that you obey the rule of 4 times of the ESR ripple as compared.
Then you don't need to put the network. That is...
That's your best case as far as
Yes.
the transient response.
yeah.
If you have enough ESR,
So
that's
the more
the
ripple injection you are injecting,
You need to inject a minimum for stability, or you need to have a minimum.
but the more you inject,
The more you inject, the more will degrade your low transient response. So if possible, always try to live with the minimum. The minimum might be dictated by the theoretical limit for stability, but also important thing, because the control is ripple based, can also be dictated by other factors like jitter or noise immunity. So you need to live with the lowest value. Your best bet is to live with the lowest value of ripple injection, provided that you satisfy stability criteria and you are relatively free from jitter.
The question is, actually, with all these highly scientific papers which kind of you rejected from the very start, but in any of those, is there like practical recommendations coming from analysis? Like, analysis and down to practical recommendation. For example, confirming what you are describing as your recommendations, like semi-practical.
Yes.
Is anything there at all, or what is it?
Well, honestly, I haven't seen too many practical recommendations. Mostly I've seen derivations. They are some of them they are key because they reveal that this type of control is in the transfer function from control to output. It's not just a single couple of complex conjugate poles, but it's 4 poles. Those are the papers from Virginia Tech. And then you have other issues that this approach will not be able to reveal. But honestly, I have not seen too many practical recommendations.
So it's a trade-off between stability and, so you try to maximize, but if it's too big, then you get stability issues.
If you are, let's say, there is a trade-off in that. If you go lower and lower in ripple self-injection, you approach the instability boundary.
Did you ever try to use output impedance measurement to reveal the limit, where you say now it's the optimal?
No, I haven't tried. That's a good suggestion. That's a good suggestion. I mean, the type of method that we were discussing in previous class, right?
Because I mentioned exactly
well,
that part, and in my opinion, the loop gain does not provide you any information, or not sufficient.
Well, if you think the loop gain is already providing you quite a bit of information in that, you can clearly see that by maximizing that ratio, the loop gain changes.
Yeah, but the phase margin is not giving you stability information.
No, that's true. For this kind of controls, the phase margin is basically you get what you get. It's not something that you can tweak with poles and zero to crank around and try to put a couple of degrees more here or there.
Maybe one more question. Is there any effect on transient, from the value of the inductor? Let's say there are other considerations how we're picking the value of the inductor, but disregarding all this, is there a kind of effect of value of the inductor on the transient?
Yes, of course. There is. There is also some impact. We've seen also some impact on the value of the inductor on the second pair of poles I was mentioning.
The same question for the value of the output capacitor. Well, disregarding that output capacitor, we are choosing, a minimal ripple or something like that, but the value itself, is it affecting transient?
Value of the output capacitor did not affect the transient. I mean, there is no limitation for the. On the inductor, we have seen some limitation above certain range value, like 15 microhenry. I think we have seen some.
So no matter how big the output capacitor is, the transient, it won't affect transient. That's
No.
what you are saying, right?
Yes. I mean, during startup, you may enter into inrush current limit. The sharp start is so low. If your output capacity is so big, but other than that, it doesn't affect.
Well,
Yeah.
thank you for all the questions.
Please